first topic in this lesson is called two-way tables. Now, we've seen two-way tables before, but we haven't really taken a chance to really break them apart and study them. So that's what we're going to do today. A two-way table, or what's called a contingency table, is a statistical table that shows the observed number or frequency for multiple variables. The rows indicating one category and the columns indicating another category. So we have two different variables happening at the same time. These conditional tables can get so crazy that you can have three variables happening at the same time. We're not going to do that today. Now, we can make our own two-way table if we have a certain data set. So let's say we're going to take some information from our own class here, and we're going to figure out how many of us wear glasses or do not wear glasses. And then we're just going to find another random variable. Another random variable we're going to do, since it's spooky season, is the people who are going to go trick-or-treating. Or those of you who are like, no thank you, we're not trick-or-treating. Okay, so we need to take an assessment of what's happening right now. If I sit here and count all of us, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 students present today in class, since we're missing a good number of friends. So that's the total number of students that will be doing this survey of sorts. So right now, I need you to raise your hand if you wear glasses. Even if you wear them at home, you don't wear them here, but raise your hand if you wear glasses. Keep them up, because we've got to count all of us. Okay, higher than that, please. I cannot see your hands. Our glasses friends are 1, 2, 3, 4, 5, 6, 7, 8 of us totally wear glasses. Keep your hands up, though. Of the people who are wearing glasses, keep your hand up if you plan on going trick-or-treating, and that counts if you have to take a sibling trick-or-treating. Okay, but we should only be having our hand up if we are wearing glasses or have glasses and want to take somebody trick-or-treating. Okay, there are 3 hands in the air, which means we're going to put a 3 in that first box, because that's where the people who wear glasses and the people who are going trick-or-treating meet up. Okay? Without having to take another survey, we should be able to fill out another piece of information. If there are a total of 8 glasses wearers in class, and 3 of them are going to go trick-or-treating, how many are not going to go trick-or-treating? 5, so we should put a 5 right here. Additionally, if we have a total of 8 glasses wearers in class, but a grand total of 18 students in class, how many people do not wear glasses? 10. Okay, cool. We filled out an entire row and column for this two-way table, but we have to take another survey to be able to figure out the rest. Okay, so this time, all my friends that do not wear glasses, raise your hand. If you do not wear glasses. Okay, keep your hand in the air. If with your hands in the air and you do not wear glasses, keep your hand in the air if you plan on going trick-or-treating or taking a sibling trick-or-treating. Which means we have 4 hands in the air. We're going to put a 4 right here. Now, how many total people are going to go trick-or-treating or take their sibling trick-or-treating in this class? 7 total. If we have 10 total non-glasses wearers and 4 of them are going to go trick-or-treating, how many are not going to go trick-or-treating? 6. And if we add up the total of number of people in class who are not going to go trick-or-treating, how many is that? 11. We have to verify on our two-way tables that the following things occur. If we add up the total number of trick-or-treaters and non-trick-or-treaters, does it equal 18? Is 11 plus 7 18? Check, done. The other thing we need to verify is that if we add up the total number of glasses and non-glasses wearers, so if we add these two numbers, do they equal 18? Check, we have a really good survey. This two-way table should always have rows and columns adding up eventually to our total in class. Okay, Now, to use two-way tables, the way we're going to be asked questions, we have to go back to the formula we used last class for conditional probability. And the way that that looked was like this. We said if we're asking for the probability of B given A, what we did every single time, even if I didn't write this formula down for this class, is you would have the probability of B and A divided by the probability of A. Here's one of the three formulas we're going to use today. Let's put a green bubble around it. Well, green for me. You can put whatever color you want. That's going to be one of the formulas we use a lot today. It's what we did last time when we did the example about the female and male soccer and basketball players. We may not have formalized it into a formula, but this is what we did. Okay. So we've made our own two-way table, so we see how this data has been collected, but then we can actually use it to answer questions about certain situations in the real world. So for example, for financial reasons, a school district is debating about eliminating a computer programming class at the high school. Don't know why, computer programming is the language of the future, but whatever. The district surveyed the parents, students, and teachers. The results, given as a joint relative frequencies, are shown in a two-way table. So this one, unlike the one we just did, doesn't tell you the total number of people who voted a certain way. It tells you their frequency, their probability, essentially. So if we look at this table, 58% of parents voted yes, and 6% of parents voted no. 8% of the total people were students, and they voted yes. 15% of the total population was students, and they voted no. 10% of the total population was teachers that voted yes, and 3% of the population was teachers who voted no. Let's find out all of our totals, because we know that's going to be helpful for answering questions. So what is the total percentage that is parents in this table? To find that out, all we would do is add these two numbers together. So what is 0.58 plus 0.06? Ooh, Friday morning, we're moving a little slow. It's 0.64. Okay, we need the total number of students or total percentage of students. How many people surveyed were students? So a 0.08 plus 0.15, 0.23, or 23% of the surveyed people were students. What percentage were teachers? 0.13, so that's 13% of the people surveyed were teachers. Let's figure out what percentage voted yes. So if we add up the entire yes row, what percentage of people in the survey voted yes? Should be 0.76. What percentage of people voted no? 24%. Now my question for you, this one's a little weird because we're giving you the percentages, like the decimal versions of the percents, but the percentages each time. So if we add up all of our rows totals and column totals, meaning we're doing this, what is 0.64 plus 0.23 plus 0.13? $1.00, yeah? And just to verify, because we know all the totals have to add up, what is 0.76 plus 0.24? It's also just 1. So it's as if we're doing out of 100 people surveyed is a good way to think about it. If you have 100 people surveyed, then 58 of the parents said yes and 6 of the parents said no. 8 of the students said yes and 15 of the students said no. 10 of the teachers said yes and 3 of the teachers said no that we surveyed. All right, we needed to do all of that because we know we need these small totals as well as our total to do a bunch of probability questions. The first question says, what is the probability that a randomly selected parent voted yes? So we are saying, or I am asking you to find the probability that the parent voted yes, again, given that they're a parent. Okay, the event A and B, just like my formula, are parent and yes. So if we look at that green formula that we put a little cloud around earlier, it says this can be found by finding the probability that a parent voted yes, so parent and yes, divided by the probability that they are a parent. Now our table already gives me these relative frequencies, so I don't have to make it fractions here. I already have the decimal fractions for each of these out of the table. So if we look in the table, what percentage of parents voted yes? What percentage of parents voted yes? 0.58. Out of how many parents? What was the percentage of parents? 0.64. All right, that's the math we need to do today to answer this question. 58% of the 64% of parents voted yes. What is 0.58 divided by 0.64? .90625, which if we round the way we've been rounding, is 90.6%. So 90% of parents that responded to my survey voted yes. Okay, just like last time when I did one of the soccer and basketball examples, you did the second one. That's exactly what we're going to do here. So problem B asks you to find the probability that a randomly selected student voted no. So we are finding the probability that a student voted no. I'll set you up this much and then I'm going to let you finish it. I want you to read the table just like we did for part A and figure out this percentage, this probability. So for this question, we are finding the probability that a student said no divided by the probability that we at least ask a student. So if we look at my table, the probability, so we have our independent events formula. Let's go ahead and write it in terms of not A and B, but in terms of what we want to know about. We are trying to see if the probability of voting yes and being a teacher, which will come right out of our table, is exactly equal to the probability of voting yes times the probability of being a teacher. Those are all different values, but they're values I can find directly out of my table. So look at your table. I'm not going to zoom to mine because I can't show both at the same time. But look at your table. What number is at the square that's where yes and teacher meets? What number is there where yes and teachers meet? 0. What? 10. Okay, great. We are trying to see if 0.10 is actually equal to the number we get when we multiply the probability from all of the yeses times the probability of all of the teachers. So looking at the table, what was the probability, it's a total, that all of them said yes? What's that total probability for yes? 0.76. What's the total probability, it's a total, of being a teacher? 0.13. Now we are actually trying to figure this out. We don't know if they're equal. If those numbers are equal, then this event is independent. If those numbers are not equal, then it is not independent. So go ahead and do that math for me. 0.76 times 0.13. Yeah, what did we get when we multiplied 0.76 times 0.13? Okay, so my question for you, I forgot one of my zeros, 0.0988. Are these two numbers the same? Don't make it weird. Are they the same?
Really, y'all? They look exactly the same.
No. Thank you. These are not the same. So if they are not equal, they are not independent events. Instead, we would call them, this is a dependent event. If those numbers, when I calculate it, are exactly the same, like the example we had last time where they were both 0.25 or 25%, then yes, they're independent events. But those are close, but not the exact same number. Don't make it weird. And additionally, conditional probability doesn't always come from when you have a two-way table. In example 2, this is going to be a conditional probability question, but I did not give you a two-way table to get the information. It says, at a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What is the probability that a student who buys lunch also buys dessert? So we are asking for the probability that a student buys lunch and dessert given that they buy lunch. L for lunch, D for dessert. Is everyone okay with that? So I don't have to write those words out. Yes. Now using my formula, we would know that the formula says for conditional probability, we are looking for the probability that a student buys lunch and dinner, but we are going to divide it, not dinner, dessert. We're going to divide it by the probability that the student buys lunch. Reading the problem one more time. What is the probability that a student buys lunch and dessert?
In the sentence, what percent of students buy lunch and dessert?
Thank you. 10%, but when we're using percentages, we don't put percents in problems. We change it back to a decimal, so we say 0.10. What probability or percent of students just buy lunch in general? 60%. Oh, thank you for responding. Appreciate it. This is 0.10 divided by 0.60. Go ahead and turn to your calculators. What is 0.10 divided by 0.60? Yeah, 0.167 if we round, which then we can change to our percentage answer of 16.7%. So conditional probability is a little bit more confusing because you have to know what has already guaranteed to happen. We're already guaranteeing they buy lunch. But out of that percentage, how much of them do something else? That's conditional probability. So again, this was a continuation of what we did last class. The definition of conditional probability is on your last set of notes, but a lot of them come out of two-way tables. On the back page, we have our last two ideas for probability here. It's called disjoint and overlapping events. I think it's easiest to understand disjoint and overlapping events with a Venn diagram idea. Okay, do y'all know what a Venn diagram is? It's like the two circles that sort of overlap a little bit. Okay, so I want you to draw a Venn diagram where it says overlapping event because we know that Venn diagrams overlap a little bit. Let me draw a better circle than that. If we let the, you know what, I'll color code mine. If we let the red circle be event A and the blue circle be event B, what do you notice about those two events? They're overlapping. So we have this section where both A and B occur. So this section, where I'm going to color it green, we're going to call that A and B. So do we see how these overlapping events have stuff in common? Now we're going to draw a disjoint Venn diagram. A disjoint Venn diagram is where you have A and B, but they don't touch each other. Do those two events have any shared things in common? Do they overlap at all? No. That's a disjoint set of events versus an overlapping set of events. Now, understanding if you have disjoint or overlapping is really helpful because it allows you to take some shortcuts in the formulas we're going to use. For a disjoint event, two events are disjoint or what's called mutually exclusive. You might see those words. When they have no outcomes in common. They don't share any common. My Venn diagram is not overlapping. When that happens and you're trying to figure out the probability of A or B occurring, you just simply add the probability of A plus the probability of B. Because they're not overlapping. So we can find this probability and add them together to say either of them could happen with this probability. So for example, let's say, hopefully we're familiar with a set of, like a regular set of playing cards. How many cards are in a regular set of playing cards? It says it on here, but if you're like playing with like solitaire or poker or any of the games you play, how many cards are in your deck? 52. There's 4 suits, yeah? What are the 4 suits?
I'll give you one. Spades.
Ace. No, not like that. I'm thinking like colors and shapes. Those are called suits.
What you give a woman when you want to marry her?
A heart, diamonds, and what else? Clubs. If you don't know those names, you can think of them as hearts, diamonds, shovels, and puppy paws. Okay? But they're called spades and clubs. We need to know those. Guys, come on. We're in high school. We should know a deck of cards. All right. A card is randomly selected from a standard deck of 52 playing cards. So regular set of playing cards. What is the probability that it is a 10 or a 4? The reason this is a disjoint event, is it possible at all for you to grab a card and it is both a 10 and a 4 at the same time? One card. No, it only has one number on it, correct? So these are disjoint events. So if we're finding the probability that we get a 10 or a 4, we calculate their probabilities separately and go about our business. How many 10s do you have in a deck of cards?
How many suits were
There's 4 10s in an entire playing card deck out of 52 cards total. How many 4s are there in an entire deck of cards? Also 4. Have we never played card games before? Oh, we haven't. Okay, so this example isn't really helpful for you. Well, there are 4 of each kind of card in a deck of cards. There's 1 heart, 1 spade, 1 club, and 1 diamond, which makes 4 of each kind. So there are 4 10s in a deck of cards and 4 4s in a deck of cards. So to find out if we randomly pull a card and it's either going to be a 10 or a 4, we just add those together. So in our calculator right now, I want you to do, without using the fancy fraction, which means you're going to have to use parentheses, I want you to type parentheses 4 divided by 52 plus parentheses 4 divided by 52. It's 0.15 and then 3 something that would round it up, so we're going to do 0.154. But yeah, which means that we have a 15.4% chance of randomly drawing either a 10 or a 4 if you just randomly pluck a card out of a deck of cards. Easy peasy. It's because they're disjoint. They can't happen at the same time. There is no card that is both a 10 and a 4 at the same time. But if we look at overlapping events, the formula adds a little something at the end. In fact, it subtracts a little something at the end. This formula, when you have things in common, looks the exact same, except there's a little extra something at the end. Instead of just adding the 2 probabilities together, what am I subtracting on the end? I'm subtracting the combination. And here's why. Although I don't know if my example is going to be all that helpful since we don't know decks of cards. When you're pulling a random card out of the deck and you want to pull either a 10 or a spade, Is it possible for you to pull both a 10 and a spade at the same time? Is there okay, maybe spade's the wrong one. Let's pretend it says hearts. In fact, we're going to change this for it to say hearts, okay? I don't think we know what a spade is.
No one in here has played solitaire, speed, anything with a deck of cards.
Poker.
So y'all seen a deck of cards. Yes, you have. Y'all seen a deck of cards.
Is it possible for you to pull one particular card and it both be a 10 and a heart at the same time? There is a 10 of hearts card, no? Which means that these are not disjoint, they are overlapping events. Because you could actually pull one card that is both a 10 and a heart at the same time. If we didn't take out that possibility, we would be double counting that card from both the 10s and the hearts. So when we find this probability, the probability of it being a 10 or a heart, we do find the probability that it would be a 10, which is 4 out of 52. And the probability that would be a heart, which my card players, the few that have admitted to playing cards, how many of each suit are there? Of each color and shape? How many hearts are there in an entire deck of cards? You have the 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. How many is that? We're going to have to play some cards in this class. That's 13 options out of 52. But we have to take away the card that is both. How many cards are both a 10 and a heart at the same time? There's one card where that occurs. I have to take it out because I would double count it if I didn't subtract it away. Because I'm counting it when it comes to the 10s, and I'm counting it when it comes to the hearts. So in your calculator, I need you to do 3 fractions, all with parentheses and not the fancy fractions. 4 divided by 52 plus 13 divided by 52 minus 1 divided by 52. We should get 0.308, and then we change it to 30.8%. Okay, we need to annotate our work a little bit, because I think if you were, especially if you don't understand a deck of cards, if you look back at this example, you're going to be like, what? So let's annotate our work a little bit. On this problem we just did, this fraction right here came from the fact that there are 4 10s in a deck. This number right here came from the fact that there are 13 hearts in a deck. The number we're subtracting is because there is 1 10 of heart in a deck. We have to take it out, or else we would double count it, since we're counting it as both a 10 and a heart. So we take out the double counting. Okay, let's leave the cards alone for a second, because obviously that's not a good example for you guys. Good life skills to know about cards. You're going to be playing cards with like anybody. It's a very good way to spend your time. So look up how cards work. Learn a card game, please, for the sake of your future. Okay. Number 3, we're leaving the cards behind. We have a whole new set of data here. In fact, it's in a two-way table. It says a vehicle is randomly chosen from a parking lot. The lot contains 3 minivans, 3 red minivans, 2 blue minivans, and 3 blue convertibles, 1 black SUV, 3 black motorcycles, 1 red motorcycle, and 2 blue little bicycles. Not motorcycles, bicycles. Find the probability of the selecting each type of vehicle. Okay, before we even start looking at the questions, let's look at our two-way table. It is telling me we have 3 red minivans, 2 blue minivans, and no black minivans. How many total minivans are in the parking lot? 5. How many total convertibles are in the parking lot? How many total SUVs? 1. How many total motorcycles?
4.
How many total bicycles?
2.
2. How many total cars are in my lot at all? 15. Okay, we're gonna put 15, and I would make this one bolder because that's our total. Okay, let's figure out the different colors. Of all the cars in the parking lot, how many are red? 4. How many are blue? 7. And how many are black? 4. All right, that is all the information we need to be able to do our disjoint or overlapping event probabilities. So the first thing we're going to do each time we do one of these problems is determine if it's disjoint or if it's overlapping. To do that, if we're finding the probability that we have a red vehicle or a minivan, we look at the table to decide if there are any overlapping events. So looking at your table, are there any red minivans? Yes. If there are red minivans, then this is an overlapping event. So we need to use the overlapping event formula, which means we're going to have to do a little bit of subtracting and not just adding. We're going to write the formulas this time because I think it would be helpful to see it on your notes, which means we're going to find the probability that we find a red vehicle plus the probability that we have a minivan, but we are going to subtract the overlap. We're going to subtract the probability that we have a red minivan. Okay, let's find these probabilities. Now, what is the probability that we find a red car? How many total red cars were there? Out of how many total cars in general? So the probability of finding a red vehicle is 4 out of 15. What's the probability that we just randomly, bless you, select a minivan? How many total minivans were there? Total. 5 total minivans out of those 15 cars. But how many were overlapping? Meaning how many red minivans did I have? 3. So I would do minus 3 out of 15. Calculator time. 4 out of 15 plus 5 out of 15 minus 3 out of 15. Yeah, so when we get this, it actually turns out to a cute number. It's 0.4, which is 40%. So 40% of the vehicles are either red or a minivan. Okay, let's look at part B. It says, what is the probability that we have a bicycle or a black vehicle? Looking at my table, if I look for where bicycle and black vehicle overlap, is there any overlap at all? Is there a black bicycle? No, so this is called a disjoint set of events. So we can use the disjoint formula, which is essentially the same as the overlapping one. We just don't do the subtracting part. Okay, so we would set it up like this. We would say, we are finding the probability that there is a bike or a black vehicle by finding the probability that we would accidentally pick a bike plus the probability that we would pick a black car. No subtraction though, because there's no overlap. They are disjoint. So how many bicycles total are there in this parking lot? 2 out of 15. And how many total black vehicles? So we do 2 out of 15 plus 4 out of 15. Again, no subtraction because they have nothing in common. We should get 0.4 again, which is 40%. So 40% of the cars in the lot are either a bike or a black vehicle. I feel like at this point we've seen enough examples to try some on our own. So C, D, E, and F are all for you to try. I'll give you about 5 minutes to try to get all 4 of them done. First, remember, you're always starting by determining if they're overlapping or disjoint so you know which formula to use or whether we're subtracting something. So C, D, E, and F are for you. Here, I'll zoom out so you can actually see the whole thing. Okay, so for part C, was that overlapping or disjoint? Overlapping, because there are black motorcycles. So we know that it's overlapping, and we're going to have to take that into account when we actually do this probability. So we would say that the probability that we found a black vehicle or a motorcycle would be equal to the probability that we picked up a black car plus the probability that we picked up a motorcycle minus the probability that we have a black motorcycle. So looking at my table, that is 4 black vehicles out of 15 plus 4 black motorcycles out of 15. Sorry, not black motorcycles, just 4 motorcycles in general, minus the 3 black motorcycles out of 15. 4 out of 15 plus 4 out of 15 minus 3 out of 15 should get you 0.333, or more accurately for me, 33.3%. For part D, is a 4-wheeled vehicle an overlapping event with being blue? Now, 4 wheels is not something that's specifically on our table in its own category, but out of the type of vehicles we're looking at, which of these have 4 wheels? Most of them. Specifically, do minivans have 4 wheels? Do convertibles have 4 wheels? Do SUVs have 4 wheels? Do motorcycles have 4 wheels? Do bicycles? So we're only looking at the top 3, boom, boom, boom. But of those top 3, are any of them blue? Do we have any numbers right there? Yes, so this is an overlapping event because there are both vehicles that have 4 wheels and are blue. So we know we're going to use that overlapping event formula. We would say the probability that we have 4 wheels or picked up a blue vehicle would be equal to the probability of 4 wheels plus the probability that it's blue minus the probability that we have a 4-wheeled blue vehicle. Okay. How many vehicles out of 15 actually have 4 wheels? We have a total of 5 minivans, 3 convertibles, and 1 SUV. We said all of those have 4 wheels. So how many total 4-wheeled vehicles do we have in the parking lot? 9. Very good. What's the probability that we pick up a blue vehicle? How many blue cars? Blue vehicles? 7 out of 15. But we have to subtract that overlapping event. So how many in the section that I highlighted in blue, or I put a little blue box around it, how many vehicles total were both 4-wheeled and blue? So we subtract 5 out of 15. I'm trusting at this point you can do the math, so I'm going to tell you right now that this would end up being 0.733 or 73.3%. All right, let's do E and F together if you haven't gotten there yet. Black vehicles or convertibles? Look at your table. Of the convertibles, are there any that are black? No, which means is this disjoint or overlapping? Disjoint. That means we don't have to do any subtracting at the end of the formula. We just get to add those numbers together without taking into account the overlap, because they don't overlap. So we are again finding the probability that it would be a black vehicle. Oh, I spelled that wrong. Or a convertible. The probability that it is black plus the probability that it is a convertible. We don't, again, have to do any subtracting because they are disjoint. There are 4 out of 15 vehicles that are black and 3 out of 15 vehicles that are convertible, which beep, beep, bop, if we throw that into a calculator, which at this point I'm trusting we can do, is 46.7 or 0.467, which is 46.7%. Part F says, blue vehicles or motorcycles? Are there any blue motorcycles? No, so is this overlapping or disjoint? Disjoint again. Again, the disjoint one is the one where there is less for you to do because we don't have to subtract out any of the overlap because there is no overlap. So we'd say the probability that we have a blue vehicle or a motorcycle would be equal to the probability that we picked up the blue vehicle plus the probability that we picked up that motorcycle. There are 7 out of 15 blue vehicles and 4 out of 15 motorcycles, which again is at 0.733 or 73.3%. So these two-way tables are not only helpful for conditional probability, which is what we did on the front, but also the probability of or statements when it comes to disjoint and overlapping events. I know that this is a lot of different formulas that I'm giving you each time, but we can keep them straight because we keep all of our notes in our green folder. So we have access to all of the formulas next to their names over and over again. Now the other piece of paper you picked up today is your homework. Look at that homework page for a second. It's just like a little classic worksheet, but then I want you to look at the little box at the top, like towards where it says date for your name. What does it say in that box? We have given you the answer key on the back, but if you just turn in a paper with those answers on it, first of all, I couldn't even do this assignment without showing work, so I know that you have to show me some work. I'm just giving you the answers so that while you're doing it, you are mentally checking to make sure that your stuff is correct. Okay? Before you get into homework time, though, we are going to do a quizzes as a review over the probability unit. So going all the way back to 13.1, it's not going to be a grade, but it's going to help me determine what's going to be on your quiz next class, because there's a quiz next class.